Well, this is our last week of CSE222. And so we've got today and we've got Wednesday. Wednesday I'm going to pretty much leave open, I think, just for questions and, you know, brief discussion of the final and whatever else we want to go over. And I'll try not to cover any new material on Wednesday. So today I want to continue talking about sorts and work our way up to heaps, which may be our last major topic for the quarter. But let's start with any questions, including questions on PA5. But anything you want to talk about or go over, let's go through that first.
Could we go over things related to what we talked about last week regarding, I think it was passing data using structures, like for showing what items were put in the bag to get the max value.
Sure. Let's see. So let's play around for a minute with structures and functions, because this is something that can be troubling. So here's just a random structure. It's got a couple of integers and a character string. And let's make a whatever variable. And so since this variable is a struct whatever, I access the fields with the name of the variable, period, the name of the field, right? We don't use arrows unless we're dereferencing pointers. So if this was a pointer to a struct whatever, we would use an arrow to dereference. And give me 1 second here. My camera is not going to work, but that's okay. You can just pretend that like I'm moving and talking. So let's call a function. And let's make a function that returns a struct whatever. So this function's going to take an integer. It's going to return a structure, right? Which means it's going to return a pair of integers and a character array. And let's just take the return value from this function and print out the fields of it and convince ourselves that this function is actually doing what it's supposed to do. I'll make a return variable of type struct whatever, and I'll set the x value equal to whatever the argument was that we were passed. I'll set the y variable equal to twice that, and I'll just load a random string into the name piece, and then I'll return that as the argument value. She should struct whatever. Ah, yes. All right. So I don't know if this will compile. It's too early to check syntax, so we'll let the compiler do it. Alright, so let's run this, right? And so when I get my thing back from my function, I've got x and y values, and I've got a name loaded in. So the point of all of this is that, you know, when you make your first version of the maxval function, it's returning an integer, and the integer is just, you know, the maximum value. It's a number. When you change maxval so that it can return a list of items and how many of each item you need to get that max value, you got to pass back more than one thing. You got to pass back the total maximum value. You got to pass how many of item 0, how many of item 1, how many of item 127. Right? So you got all these things you need to send back to the caller. That's this. And so if we make a structure that contains all of that information, the maximum value, the array of item counts, we can just return that from the end of maxval and save it, you know, in a structure of the proper type, and we're good to go. So what exactly does that look like for the maxval function? So I've been calling this a struct answer. But as I mentioned in Discord, right, you don't need structures at all. You can do this with no structures anywhere in sight. Structures are just kind of a convenience. It's a way to take a group of things and treat them as a single variable. And since C functions only return one variable as their function value, if we make that variable something of type, you know, struct answer, we can put a whole bunch of things into it, like 128 item counts and a maximum value. And so that's why I've been doing this, but it's not strictly necessary. I could pass these things by address as arguments, and I could get those back, you know, through the parameters. But that's a little quirkier to do in C, and this is really kind of a natural way to use a structure, to take things that sort of logically belong together and treat them as a single thing. And that's where we're going, you know, in April when we get into 223 and we start doing Java. We're going to be thinking about not, you know, here's 20 random variables, but here's a thing that contains, you know, 20 pieces of information, but we want to treat it as one thing, which we're going to call an object. And so this is a nod to that. So, you know, maxval, basically we need to pass the capacity. And you also, you know, need to tell your maxval function what the list of items you can choose from is, what their names and weights and values are, so you pass that information too. And that can be, you know, separate arrays, or it can be an array of structures or whatever. But the new piece here to go from just a maxval to a maxval and item counts is that your maxval returns a structure. And so inside here, you're iterating over all of the items that you can choose from. And so in the just integer version, we had something like, you know, best equals value of item I plus maxval capacity minus weight of item I. And so we're still going to do that. We're going to do maxval of capacity minus weight of whatever this item is. And if this is an array of structures, you know, it'll be item array bracket item dot weight or something like that. So do the C syntax. This is the value that we get out of the bag after we've put item number item into it, right? And we don't care just about the maximum value. We also care about the count of how much of each item we need to get this. So, you know, make a struct answer temp equal to that. So this thing contains the maximum value. It also contains the inventory count. And we need to record as we iterate through this loop the best maximum value that we've gotten. And so we need some kind of, you know, variable inside here. It used to be an int best. Let's make that a struct. So a struct answer best. Make sure you initialize this answer to 0. How do you do that? Set the value to 0, set the count of all 128 items to 0. So don't just assume they're zeroed out. So put something in here, you know, that goes through and sets each of those item counts to 0, sets the max val to 0. And then, you know, when we get the max val back from here, we can do something like this. If best value is less than value of this item plus temp dot value So this is the value of this item. This is the best value we can get from our bag once we put that item in it, right? It's the value of this diminished capacity bag. So if the value of this item plus the value we get from the remaining space gives us a total value better than the best value we found, then we want to copy temp into best, right? So that copies the item counts, and this is clunky the way I'm writing it, but you know, I would set best value equal to value of that item plus temp.value. So this copies the solution for the diminished capacity bag. This adjusts the value of that solution by also adding the value of item I, or item number, and then best dot item counts, if that's the name of the array of how many of each item you need. Let's take the item indexed by this and bump that up by 1, because what are we doing here? We've added item to our bag. And so iterate over all of that and then return your best solution.
How does this affect saving the max val result to an array of previously calculated max values?
Okay, good. So after this is settled, right? You want to do dynamic programming. Instead of just saving the max val, we need to save, you know, these answers that we're getting back. So we do something like this. Instead of an integer array, we have, you know, a global outside, which could be, you know, struct answer save 1025. make sure you initialize this somehow. And the way I've been suggesting to initialize is just set the value of each item to -1, because you know that's not a valid value. And so in the beginning here, right, before you do any of your iteration, check to see if you've already saved this value. So what does that look like? You know, if save bracket capacity dot value is bigger than or equal to 0, then we've already calculated the solution for capacity. We've saved the struct answer in this array at index capacity. So just return save bracket capacity. That is a struct answer, and it's the one that we would have saved at the bottom. If we haven't saved it, we go ahead and we do all of this calculation, and then at the bottom we save the answer. And so what does that look like? So there's the whole iteration. Here's where we save the answer. Save bracket capacity equals this thing we're about to return, which is best. And that's it. It's one line in the beginning, it's one line at the end. Nothing else in here changes, right? In the very beginning, before you do anything else, before you check basis, before you do anything, right? As soon as you come into the function, say, hey, I'm trying to find max valid capacity. Have I already done that? So check your save array. If you've got, you know, a structure of some other type in here and you're setting valid flags or something, whatever you're doing, check to see if you've already saved an answer for that capacity. If you have, return it. If not, do everything exactly the same way. Don't be checking your save array in here. Don't be writing to it or anything like that. Just do your unadorned loop, right? And at the very end, before you return, just save your return value into your array.
So I have a question about the heapify.
Okay.
Hey Sam, you're my phone. What? Oh, is I just Sam? Or, yeah, sorry. That's alright. My question was that when I was, in order for me to call the recursive function, do I compare the inventory weight to the capacity? Because when I did that, it will run again and give me return a higher possible value because the weight will continuously be less than the capacity until it reaches, you know, and so forth. So I feel like I'm not doing the algorithm right, but I'm wondering if that's the right comparison.
So we should do this only if the weight of this item is less than or equal to the capacity. That's the only time we want to do all of this business.
Oh, I should, that needs to go outside my for loop then, huh?
Say again?
That goes outside the for loop?
No, it's inside the for loop. So it's an item by item question. So here's item 0. Does it weigh more than the bag can hold? If it does, I'm not going to do anything with item 0. Go on to item 1. Does it weigh more than the bag can hold? No, it weighs less or the same. Okay, let's go ahead and say if we put that item in, how much value do we get from the remaining space? And if that's better than our best answer, then we'll say, okay, that's our best answer so far, is to use item 1. Go on to item 2. If it weighs more than the capacity, skip it. Go on to item 3, and so on.
Okay. The reason I'm asking that is because I'm in GDB right now trying to debug my program, and the issue is that I got the right value, but then it will check inventory weight with capacity, and because less than that, it's going to increment it, and it's going to kind of do another extra run, causing it to add more than what it's supposed to be.
So what do you mean it's going to increment it? What's it going to increment?
Well, so I compare inventory weight with capacity, so I get the right value, but the weight I checked was 2, and the capacity is more than 2, or sorry, yeah, it's more than 2.
Okay.
So it will kind of it'll run it again after I get the right answer for some reason. I'll have to go in office hours, but that was just kind of my biggest issue right now.
Yeah, so you're doing this check before you ever do any other calculation with this item, right?
Mm-hmm.
So don't calculate this first and bump up your counts and then check this, right? Check this before you do anything with that item. And if the item weighs too much, don't calculate the temporary max val, don't add the value, don't compare to the best value, don't adjust the item count. Skip all of that. Just go to the top of your loop and go on to the next item.
Okay.
But yeah, come by office hours and we can look at specifics. I don't know why my camera's weird, but it's freaking me out. So I'm getting rid of it. All right, cool. Other questions, other issues people are running into? Make sure you do this initialization. There's some environments people are developing in where things get zeroed out automatically, and if that doesn't happen on the server, you're likely to get really bizarre answers when your code runs there. And zeroing out the max val itself is not sufficient. This is a hard algorithm to kind of debug with print statements or even with GDB because of the recursion, because you need to really keep track of, where you are, and the nature of the problem, the whole reason it's a good problem for dynamic programming is that you end up calling function values so many times that if you want to debug this part of it, really the only thing you can do is go through the algorithm on paper, make a clear record of what should be called when and what should happen inside each of those calls and what should be returned, and then step through line by line in GDB and make sure that's exactly what's happening. That's if you're lucky enough to get it to fail on a simple test case, right? And you might want to do some experimenting, bags with low capacities, small number of items, and see if you can find something where there's only a dozen recursive calls, but it still fails to give you the right answer. If you got that, you're all set. You can go through the worksheets and figure out what should be happening, and then compare it to GDB line by line. GDB is still really useful, if you're having trouble building the inventory of items in the beginning, you're reading in the flat file, things like that, right? That's totally fine. But once you get into recursive stuff, it can be, tricky to pin down by putting in a bunch of print statements or something. It's possible, but it's painstaking. All right, any other questions, comments? All right, well let's continue talking about sorting. And so we went through a couple of, or 3 different order n squared sorts last week. All right, so if I'm doing a selection sort, and here's my array of data that I'm sorting, what's the first thing I'm going to put into my output array for a selection sort? What's the first number that's going to appear in the output? And I'm sorting smallest to largest.
A 1?
It's going to be a 1. Selection sort, you do your work when you choose which input element to put in your output. So first you're going to put in a 1, and then you're going to put in a 2, and then you're going to put in a 3, and so on and so forth. For an insertion sort, what's the first number that's going to appear in the output?
A 2?
It's going to be a 2, because insertion, we don't do any work in selecting. We just start at the beginning and we go down the list. But when we take each of these and we put it in the output, we put it in the right spot. So this is our linked list sort, right? We take the first thing, we put it in the 2 because it's the only thing in there. We take a 4, we're going to put that into our output list, but we're going to put it in the right spot, so it's going to come after that. So our second list would look like this, and then a 6 would look like this, and then when we get the 1, it'll look like this, and so on. And so those are both order n squared. And we know these sorts intuitively. We learn these somewhere along the way. So when I do in-person classes and I'm grading homework, right, and I've got all the papers graded and I need to enter the grades, I need to alphabetize the pieces of paper, right? And I do that by basically, I go through the stack of assignments and I build an output pile that's in the right order. So I take the first assignment, I put that in my output. I take the second one and I put it before or after that first one. And I take the third one and I put it before or after the first, second, or third one. And so on. And so I seem to sort of naturally do an insertion sort when I'm working with physical papers. It's the same amount of work as a selection sort, but it feels more natural somehow. I think my process of, putting my papers down so I can see all the names makes it easy to grab one and insert. I don't know. If I have 60 students and I'm trying to alphabetize them so I can enter grades into something, what does an order n squared mean? Right, 3,600 operations I'm performing just to alphabetize those papers. That's a lot of work. If I could do one paper a second, that's an hour just to alphabetize. In reality, it probably takes me about 10 seconds to take a page and find where in the output list it should go. That's 10 hours, right? So an order n algorithm would be much nicer. So when I do this with physical papers, I don't do, an insertion sort on all 60 papers. I do it on, maybe 15 of them. And 15 squared, that's a smaller number. That's like 225 or something. That's more manageable. And then I get, little stacks of sorted assignments, and then I have to put them together. That's where we come into a merge sort. So, a pure merge sort, you sort the subpiles by using a merge sort. But as long as you've got two sorted piles, you can interleave them together into a sorted output. And that's an order n operation. You have two piles, you just pull off the top thing from each pile, whichever one is smaller, and you add that to your output. Alright, so a pure merge sort takes an array, and we did this the other day, right? So I'm just rehashing. Split data into two halves, A and B. Merge sort A, merge sort B, and then mix those sorted lists together to get your output data. So the only real work in here, other than making a function calls, or revisioning your data as being in half, the only real work is being done right here, which is an order n operation. If you have n pieces of data coming in, then each of these has length n over 2, and you have to go through all n of those pieces to figure out which ones go in your output. And so the question is, how many times do we recurse? Well, each time we call merge sort, we split our data in half. We have a base case. Which says, if the data has a length of 0, just return. So we basically recurse until the data gets down to a length of 0 or 1. And the number of times we recurse is on the order of log n, where n is the number of pieces of data. So we do this operation log n times, so merge sort ends up being n log n. Alright, so questions about merge sort.
So merge sort is pretty dang efficient then.
It's very efficient, yeah.
So n times log n, yeah, that's going to be a really small number, right?
Yeah, I mean, order n would be more or less the reasonable limit to how fast we could go, because if you got to sort n pieces of data, you imagine you have to at least touch each piece of data once. So, n is kind of an ideal, and log n is a small multiple. I mean, for 1 trillion pieces of data, this is order 40 times n, right, which is basically linear. So yeah, this is a cool sort.
For the smaller numbers, it's actually less than n, right?
Log n, well, I don't know.
Like log of 2 is 0.3.
So this is always log base 2, actually.
Oh.
So, but we don't really worry about constants for the most part. Like even if this came out to be, order 10 times n, right, which is the same order as n, it could be that, some other sort that's order smaller complexity might take more time. It might have a bigger multiplicative factor in front of it. So one of the disadvantages of this is our data moves a lot. Since we're constantly splitting our data in half and passing each of these to a function, potentially our data shifts around memory quite a bit, and that can have negative impacts on cache performance and things like that. But it's still good for an n log n. So another n log n is called quicksort. You can tell quicksort had a better marketing manager. So quicksort is a very quirky algorithm, and I'll run through an example of using quicksort with you. And it may not make a lot of sense, but you got to kind of play along. You got to ask questions like, wait, why are you doing this? Right? If you just kind of sit back and watch this and don't think about it, I guarantee when you try to look at it later and reproduce it, lots of questions are going to come up. And when I ask you to do this on an exam, that's not the good time to wonder about, wait, what do these arrows mean, and so on. So ask questions as we do this. So here's a set of data. I got 10 numbers here. And our goal is to sort from smallest to largest, same as usual. And a quicksort takes the following strategy. It says, let's pick one number, which we're going to call the pivot, and let's figure out where that pivot should go in the output array. Now we can start with any number we want, but typically we start with the last number in the array. We're going to pick this number right here, and I'm going to draw a box around it. I'm going to say this is the pivot. And we're going to make a series of passes through quicksort, but basically what this pass is going to do is put the 17 into the right spot in this array. And we're not going to worry about where all the other things are. We're just going to figure out, hey, if we were to sort this whole array, where would the 17 end up being? And so we can take a sneak peek and say, if I were to sort this, what would we have? We'd have a 1, an 8. I'm going to mess this up. An 11, a 14, nope. An 11, a 12, a 14, a 17, 19, 23, 55, and 60. So if we had some clairvoyance, we could say, okay, the 17 should end up right here. Okay. The goal of this pass of quicksort is to figure out efficiently where that 17 should go without having to sort our data first. Yeah, go ahead.
So, would this be like an array of integers and you just put in the 17 at the correct spot? Is that kind of the idea?
That's the idea, exactly.
But what happens to the number that has already occupied that spot?
Oh, it's going to go somewhere else. And we're not going to worry about that, but it's going to end up that the 17 will be in that spot, and the 55 may go somewhere else.
So, is the idea basically to set a pivot to a number, 17 in this case,
Mm-hmm.
and then basically go through the list and see which, decide whether or not a number goes before 17 in this case, or after,
Mm-hmm.
and then and so just put like the pivot at the end to start with, and then move it to the beginning, and then wherever else is needed.
Yeah, so that's effectively going to be the end result. And this is going to be an order n operation. And basically by going through our array once, we're going to end up with 17 in the correct spot, but we're also going to end up with something else. We're going to end up with everything over here being smaller than 17, and everything over here being bigger than 17. And this half is not going to be sorted, and this half is not going to be sorted, but we know the 17 will be in the right spot. And everything here will be on the right side, the proper side of 17, and everything here will be on the proper side of 17. So let me show you how this pass works. But keep in mind the goal, right? The goal is to get 17 in the right spot, make sure everything to the left is smaller, everything to the right is bigger. So we begin with the left side of the array, and our goal is that, everything to the left should be smaller than our pivot. So we say, is 12 smaller than our pivot? And the answer is yes. So 12 can stay right where it is, right? Doesn't matter if 12 should be the first number or not, but we know we want it to be somewhere to the left because it's smaller than our pivot. We move to our second number, which is 23, and we compare that to our pivot, and 23 is too big. 23 does not belong over here on the left side of the array. It belongs somewhere on the right. Well, we could just swap it, with this last number, but, 19 also belongs on the right, so we're not going to do a swap. We're going to start here. Compare the 12, it's smaller, leave it where it is. Compare the 23, it's too big, so we're going to have to move 23. We're going to hold that spot in the back of our brain. We're going to start over here at the right side, and we're going to say, let's compare this to our pivot and make sure it's greater. So if 19 is greater than 17, no problem. Let's move a little further to the left and look at the number 1. 1 is not bigger than 17. So now we've identified two things. We've identified a 23, which is too large, and we've identified a 1, which is too small. We're going to swap those. So we're going to copy the 23 over here. We're going to copy the 1 over here, which is going to make our array look like this. 12, 1, 11, 14, 60, 55, 8, 23, 19, 17. And we've dealt with these numbers so far. Okay, once we've done our swap, we go back to the beginning. We start from our leftmost number and we look at the 11. 11 is smaller than 17, that's fine. Move to the next number. 14 is smaller than 17, that's fine. Move to the next number. 60 is too big. So hold that in memory, come over here to the right and start looking at numbers. This should be a number bigger than 17, it's not. So those are in the wrong order, we swap them. And now our array looks like this. So that becomes an 8, a 55, a 60, 23, 19. There's our pivot. And we have now dealt with all of these numbers. And we go back and we do it again. Continue from the left, look at the 55. That's too big. So we're going to want to swap that. Go to the right. 55 is the number that we just looked at from the left. Our two direction arrows have collided. We're done. And we ended up in this space right here. So now we swap this and the pivot. And our final array after this one pass is the following. And I'm going to circle the pivot that we just moved in to say that's in the correct location now.
Wait, how did you know that 17 goes right at 55? I'm thinking no.
Because we were moving from the left, we were moving from the right, we got down to here, and then when we did our swap and we continued, we moved to the left, stopped because that was too big, we moved to the right, we collided with the arrow from the left. That's the end of our pass. And where our two arrows are pointing, that's the number we're going to swap with the pivot.
Okay.
And so 17's in the right spot, but the really glorious thing is all of these numbers are smaller than 17. All of these numbers are bigger than 17. Well, this is a smaller list than our original. This is a smaller list than our original. So how do we finish the sort? Just sort this and sort that, and we're done.
Question.
Yeah.
Would the operation still be before n if instead of like when you found a value to the left of the pivot that was greater than the pivot instead of starting from like where the pivot is on the right in this case and then moving left, would it increase? Would it be an increase in order of complexity if instead of doing all that you did you moved everything in the list left one space, including the pivot, and then that value that's greater than the pivot you just moved to where it was before?
If I understand what you're asking, if you start moving elements of the array, like large numbers of elements, you're adding an order n to that part of the operation. So swapping a pair of numbers, whether they're numbers like this or numbers like that, that's a fixed amount of time. That's like 3 operations. But if we were to try to take a chunk of data and move it down to make space for something, that will increase our order of complexity. If we only did that at the very end, if we moved all these things down and put the 17 in, then that would still be an order n in the end. It would have a higher constant in front. But we don't really gain anything by putting the 17 here and moving things down, because we don't know what the order of this is anyway. So we may as well just swap them. Alright, so the final question is, how do we sort these smaller lists? What's the magic answer?
The same sort.
Yeah, use a quicksort. So good old recursion comes back. So a merge sort, right, the idea was split your list in half, merge sort each half, and then mix the results together. A quicksort, the idea is take your original data, make one pass through it to basically get everything to the left smaller than a pivot, everything to the right bigger, and then call quicksort on each of those half lists. And when you're done, your whole array is sorted. So here's you know, what we expect the list to look like in the end, right? And if we sort these 5 numbers, we're going to end up with this. If we sort those 4 numbers, we're going to end up with this. The 17 will stay where it is, and we've got our sorted list.
I don't know if you said this already, but is this are these sort functions in a standard library or a C library in general?
Depending on your system and your language and so on, yeah, you can certainly find standard implementations of all of these functions, and you know, a lot of times if you're doing a lot of heavy sorting, there's functions already, there's programs already made for that. But yeah, you should be able to find implementations of these. And I think the C, the Linux sort, I think is a quicksort. I'm remembering that in the back of my brain. Nope, doesn't seem to say in here. But I think that's a quicksort. All right, so let's go through a few more examples of this, just to kind of nail down the mechanics of what's going on. So we got 11 people in here. Give me 11 integers. Everybody give me your favorite integer. Reasonably small integer. Say again?
4.
4.
131.
Nice. See, I got an 8 and a 51 in chat. This would be a good exam question. Tell me your favorite integer.
18.
18. I'll throw in some. I don't know, throw in a 20. All right, so which number is the pivot? I am not putting that number in.
It could be any number, but I guess 20 would be.
Yeah, so we're just gonna stick to using the last number as the pivot.
What would be the big difference if you were to choose a different number for a pivot? How would that impact the algorithm?
So certainly choosing the first number would be pretty straightforward. But if I happen to pivot, you know, in the middle, it's just kind of weird to keep track of as you're moving through. Make sure you don't, you know, consider that number and compare it to the pivot. So we usually just throw it on one of the ends just for simplification of this piece of the algorithm where we're moving our arrows in. But I think if you pick the first number, it's exactly the same kind of look and feel. All right, so we're going to start from the left, right? What's the first number that we're going to find that's out of order? That is a palindrome. Cool.
If you're starting from the left, then 131.
Yeah, so we'll start at the left. We're comparing numbers to the pivot. 4 is okay. 131 is on the wrong side, so we're going to stop there. And then we're going to begin with the 9. And we're going to find already the 9 is on the wrong side of 21. And so these two numbers have to exchange with each other. And so we do a swap and we get the following. We get 4, 9. The other numbers stay the same. All right, what do we do next?
Iterate from the left.
Okay.
And the next one is 51.
All right, good. So we're going to continue from the left. We look at the 8. 8's okay. It's smaller than 20. We look at the 51. That's incorrect. It's on the wrong side of 20. We're going to stop there. What do we do next?
Iterate from the right, from the last point on the right.
Okay.
Do the same thing from right to left.
Okay.
Which is a number greater than 20.
So from the right, we stop when we get to a number less than 20.
Oh, the opposite?
Yeah. So coming from the left, we're looking for things that we're going to keep things that are smaller. We're going to stop when we get to something bigger. From the right, we're going to keep things that are bigger. We're going to stop when we get to something smaller.
Yeah, that makes a lot of sense.
Okay.
The biggest number on the right.
Yeah, we want bigger numbers on the right, so we want to swap this number that's too big with something over here that's too small. So we'll stop at the 7, and we'll swap those with each other. This becomes a 7. Our 51 goes over here. There's our pivot. And we've done our numbers this far. Alright, and we go back to the left, and the same idea. 18 is fine. 37 is too big, so we swap. Start from the right. 11 is too small, so we're going to swap the 11 and the 37. It's going to give us a 4, 9, 8, 7, 18, 11, 37, 51, 131, and 20. And so we have, two pointers. I'm drawing the old pointers in there, but we've got 2 pointers, and right now our left pointer was here, and our right pointer was here. So we're going to bump this up to right here, and we're going to collide with our other pointer. So now both of our pointers are pointing at the 37. That means we're done, and we're going to swap the 37 and the 20, the pivot. And so our final value of our array will look like this. So the 37 swaps with the pivot. And this number is now in the correct location. So all of those are less than 20, all of those are bigger than 20.
Would it help if you kind of write down the algorithm in words? So just because when I'm taking notes about this, I'm going to come back and forget what I wrote down.
Yeah, let me do that. Hold on one sec. All right, so yeah, what's the pseudocode look like? So quicksort an array of data. So let's see. And I'm going to think of my data as I'm going to assume I've got n plus 1 pieces of data in here, just so we don't get too crazy with indices. So my left index, my left arrow is going to start off at 0. My right arrow is going to start off at n minus 1. My pivot is going to be element n. And then, I don't know, you could do something like while left is not equal to right. I'll make this sloppy pseudocode. If data left is bigger than the pivot, nope, let me do it like this. Well, data left is less than data pivot, and left is less than right. So start off with our left equals 0. If this thing is smaller than the pivot, and if we haven't collided with the right arrow yet, just move the left pointer. Once you've gotten to a point where either this number is bigger than the pivot or left is equal to right, let's move in from the right. So let's say while data right is bigger than the pivot, and right is bigger than left, let's move to the left. And then if left is not equal to right, swap those two elements, swap data left with data right, and go back up here. Otherwise, we're done with that pass, so swap data, and left and right are equal to each other, so we could use either one. Swap data left with data pivot, and then qsort data 0 through left minus 1, and then quicksort data left plus 1 up through whatever the last element is, n. So this is obviously not C code, but this is a description of the algorithm, right? So start from left equals 0, right equals the thing on the end of the array, pivot's the last element. Well, the left arrow's pointing to something smaller than the pivot, and we haven't hit the right arrow, just move the left arrow over. Once we leave that loop, iterate as long as the right arrow is pointing to something bigger than the pivot, and the right arrow hasn't hit the left arrow, keep moving the right arrow to the left. When we're done, if left and right haven't collided with each other, swap the things that the left and right arrows are pointing to. So do that, reversal, then go back up and continue. This will continue until the left and right arrows have collided, at which point we swap the thing that those arrows are pointing to with the pivot, and then quicksort the two subarrays. So yeah, this is a different kind of sort. I don't think I've ever voluntarily coded a quicksort. I might have done it in school and blocked it from my memory. But it is a very efficient sort.
Question?
Yeah,
I'm sorry, I didn't know your school story, but
it's okay.
So I'm trying to read your handwriting. Is that qsort data 0 to left minus 1, and then qsort data left plus 1 to n?
Yeah.
Okay.
Yeah, so that's the point where our arrows have collided, and so this is what left and right are both equal to. So now we quicksort from the beginning up to right before that element, and then we quicksort from right after that element to the end. And this doesn't make sense in most languages. We can't say 0 ... left. Probably in Python you can, but in C we can't do that. But that's just pseudocode. So sort the left half and then sort the right half. And then once they're sorted, we're done. We don't have to put anything together. If we sort those 5 numbers and we sort those 4 numbers, we're all good to go.
So in that case, we should make the recursive function like, well actually, is that what we did it in the pseudocode? Is we call the, call store data left, store data right?
Mm-hmm.
Is that what we did? Okay.
Yeah, that's the recursion right there.
I see. Still getting used to the recursive stuff.
Yeah.
But it makes more sense by going to GDB, but then it just the magic really happens when it hits return, which is kind of funny to me.
Yeah, someone mentioned that in Discord, and I thought that was a clever observation, that the recursion sort of makes sense once you hit return. And that's really where, the kind of magic happens. That's where the calculations sort of take place, which is a little strange. All right, so what's the order of efficiency of a quicksort? It's similar to a merge sort. Each pass is order n. And once we finish a pass, if our number goes in the middle, we split our lists in half. And the base case for a quicksort is if you're asked to quicksort something with only one number in it, just return. There's no sorting to be done. So the number of passes is how many times we have to split our list till we get down to a list of size 1. And if we're splitting our list in half each time, that's on the order of log n passes, and each pass takes n, so this looks like an order n log n. Under good circumstances. But things can get pathological. And they get most pathological when your data is sorted to begin with. So suppose my data looks like this. So here's my pivot. And I'm going to start off with my 1. And that's smaller than my number, and I'll go to 2, and that's smaller, and 3, 4, 5, 6, 7 is smaller than my number, and I run out of things, right? That tells me my pivot's in the correct spot. And so now I know that everything to the left of this is smaller than the pivot. Everything to the right, which is nothing, is bigger. And so the 8 is in the correct spot, and now I call quicksort on this array. And so I'm going to set this up to be the pivot, and I'll start moving from the left, and smaller, 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 and I get all the way over here. I know my pivot's in the correct spot. And now I call quicksort on this array. And each pass is still order n, but I'm going to end up doing n passes on my array, because after each pass, all I've done is reduce the size of my array by 1. And so if my data is sorted or nearly sorted to begin with, I have the following bad behavior. Instead of my pass splitting my data into 2 halves, it's reducing the size of my data by 1. It's saying first I've got to quicksort 8 things, now I've got to quicksort 7 things, now I've got to quicksort 6 things. And that's like a bubble sort. This is going to end up being order n squared. And so quicksort has this weird behavior that it works faster on data that's randomized. Now bubble sort, if your data is sorted or mostly sorted to begin with, and you kick out of your sort as soon as you realize you haven't swapped anything, bubble sort can be a lot faster on data that's almost sorted. Quicksort will generally be worse. And so sometimes with a quicksort algorithm, before you begin sorting, the code will actually randomize the data. It'll shuffle it around a few times to make sure that if it happened to be sorted to begin with, it's not sorted anymore. And if it was randomized to begin with and you shuffle it up, it's probably not going to randomly sort it. So sometimes quicksort includes a extra shuffle operation in the beginning to make sure your data is stirred up. And that's just for the sake of making sure that each pass you split your data close to in the middle. And so that's kind of weird. All right, any other questions on quicksort? Let's really quickly do radix sort, and then we'll take a break and we'll come back to heaps. So radix sort is based on sorting the, for example, decimal representation of your numbers. And so let's take these numbers and let's sort these using a radix sort. And these are written as integers, but we're kind of thinking of them as strings. We want to look at the individual digits in these numbers. And so there's a small chance I will get this backwards. But we'll have faith. Let's start with the rightmost digit. And here's what we're going to do. We're going to sort these numbers just based on this one digit. And one way to do this, since we know we only have 10 digits, is to simply go through this list of numbers 10 times. And the first time through, we'll pull out anything that ends with a 0. The next time, we'll pull out anything that ends with a 1, and so on. So if I'm just sorting on this least significant digit, let's go through, let's pick out all the things that end with a 0. So I've got a 500, and I've got a 420. And then let's go through and pick out all the things that end with a 1. So I've got a 421 and a 221. And then go through and pick out the things that end with a 2. So there's my 222. Pick out the things that end with a 3. So there's a 123. pick out the things that end with a 4, 5, 6, and 7. There are none of those. Pick out your 8 is 128, and pick out your 9 is 619. And there we go. That's our data after one pass. All right, now we move to the second digit. And you can sort this however you want, but again, an easy way to do this is just make 10 passes through here. So I'll pick out the things that have a 0 in this position, then I'll pick out the things that have a 1 in this position, and then I'll pick out the things that have a 2. I didn't realize I liked 2s so much. I think I lost something. 420. All right, and then finally we go through and we sort by most significant digit. And so we'll pick out the numbers that begin with a 1, so there's 123, 128. Numbers that begin with a 2, there's 221, 222. Nothing begins with a 3, numbers that begin with a 4. Numbers that begin with a 5, and numbers that begin with a 6. Bingo, our data is sorted. Really fast sort, really easy to code if you have a way to get to digits. Would be a good way to alphabetize things potentially. And if I had some 2-digit numbers, I can just, put zeros in the beginning of them and order those appropriately. And what's the order of complexity of this? What's the order of complexity of sorting these numbers by one digit?
1.
It's 1. No, it's not 1. Because 1 would be the same amount of time no matter how much data I have. But yeah, someone said in chat, it's order n. If you have n pieces of data, I have to make n times 10 passes through this data to get my output list. So I can just go through and I can pick out everything that begins with a 0 and put those down, everything that has a 1 and put those down. After 10 of those passes, I've sorted by that digit, and each pass takes n operations. So this is order 10 times n, which is the same as order n.
How would you compare the numbers with the other numbers?
So I'm instead of sorting, just taking these and sorting them, I'm doing basically a selection sort. But it's a peculiar selection sort where I'm deliberately doing more work than I probably have to, but I know that the smallest numbers will be the ones that end with a 0. So I'll simply go through, and anything I find that ends with a 0, I'll just copy that to the next place in my output. And then I'll go through and I'll find everything that ends with a 1, and each of those I'll copy to my output, and so on. So each pass is order n, and if I assume my numbers all have 10 digits or fewer, I have to do 10 passes, so my total order is 10 times n, which is still order n. So this looks like an order n sort, which would be really cool. But is this really better than a quicksort or a merge sort or sorting with a binary tree? Maybe, but we rarely use radix sort. So I'll let that linger in the air. Let's go ahead and take a 5-minute break. and think about that. If radix sort really is order n, why isn't this the sort we use for all of our sorting needs? And the answer is it's not actually faster than a merge sort or these other n log n sorts. So think about that, and we can talk about it next time if we want. But let's take a 5-minute break here, and then we'll come back and we'll talk about heaps.
I would have thought it was definitely linear, but could only be used in specialized cases.
All right. Questions on radix sort? All right, well, let's talk about heaps. And so heaps are a tree-like structure. They're a binary tree. They're not a binary search tree. So it's a tree, each node has, 0, 1, or 2 children. There's a left child and a right child. But there's no predefined relationship between a root node and the values of its children. There's no significance to being on the left or being on the right. Unlike a binary search tree where values to the left are smaller than the root, values to the right are bigger. And there's two kinds of heaps we can talk about. There's max heaps and there's min heaps. And they work exactly the same except opposite. And so for no particular reason, we're just going to talk about max heaps. But everything that we say about max heaps, we could make a similar statement about min heaps, but we sort of swap around, larger for smaller and things like that. But we'll stick with max heaps so we don't confuse things. So, what is a heap? So it's a binary tree. It has a heap shape, and we'll say what that means. And each node satisfies the heap property. So it's a binary tree that has the heap shape and in which each node satisfies the heap property. Alright, so what is a heap shape? Boom, 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 boom. There's a heap. That's also a heap. That's also a heap. That's also a heap. The heap shape means every level is completely filled in, except possibly the lowest level. And the lowest level is filled in completely from left as far to the right as the last piece of data. So every level is completely filled, except possibly the deepest level, which is filled in completely starting from the left. But if I only have 9 things in my heap, right? I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes in my tree. I can't have any more. I can't have, something hanging off of these. But if I were to add a 10th thing to my heap, it would have to go right here. And if I add an 11th, it's got to go over here, and so on.
So can a heap be unbalanced?
I don't think a heap can be unbalanced.
Okay.
So another way to describe the heap shape might be to say it's, balanced and some other property. Because I could put one node off here and that tree would still be balanced, but it wouldn't be a heap. So another way to think of this is that if you were to start filling in the nodes of a heap, you basically move from left to right. And when you get to the end of one level, then you go down to the next level and you start filling in from left to right. Alright, so that's the heap shape. And every time we have a heap, it's got to have this shape. If it doesn't have the shape, it's not a heap anymore. The heap property, and this is for a max heap, each node is bigger than I'm just going to say bigger than. I think we can do heaps where there's multiple occurrences of the same number, but I'm not going to get into that. So we'll just say each node is bigger than both children. If it has two children, it's bigger than its only child if it has one child. If it has no children, it automatically satisfies the heap property. So I'll just put all in parentheses. So the max heap property says each node is bigger than its children. Alright, that's all you need to be a heap. So let's see an example of a heap.
I'm kind of curious, what's the major differences between the binary tree and a heap, if a heap is just a balanced binary tree?
Let me draw you a heap and we'll see pretty quickly why it's not a binary search tree. Here's 100, here's 90, here's 50. There's a heap. So it has the heap shape. Everything's filled in except the bottom level, which is filled in from left to right. And each node is bigger than each of its children. But it's definitely not a binary search tree.
I see, because it's not organized to be a binary search tree.
Yeah. So here's something that's bigger than the root. Or smaller than the root, even though it should be bigger. And in fact, it's guaranteed to be smaller than the root. And here I've got, a bigger thing on the left. Here I've got a bigger thing on the right. Here I've got something, in the left subtree that's actually bigger than these things in the right subtree. But that makes it pretty easy to build a heap, because we don't have to worry about moving things around left to right. We just have to make sure that from top to bottom, each node is bigger than both of its children. And this heap property is kind of recursive. If we know that every node is bigger than its children, well, 57 is guaranteed to be bigger than these. And since 90 is bigger than 57, 90 is also bigger than both of these children. And since 100 is bigger than 90, 100 will be bigger than both of these children, and these children, and this child. So 100 will be bigger than all of its children or descendants of its children. And so each node is actually bigger than, all of the nodes underneath it. But because inequalities are transitive, all we have to do is compare each node to its two children and make sure it's bigger than both of those children. Or, it's one child or it's no children. I'll throw one more node in here just so we know we can do that. There we go. Alright, so that's a heap. And if you have a heap, it's a really nice way to pull data out in sorted order. So what we do with a max heap is we extract the largest thing in the heap. That's our main operation. Remove one thing from the heap, and we want that one thing to be whatever the largest thing in the heap is. With a min heap, each time we remove the smallest thing from the heap. So that's the life of a heap. Someone says, give me your largest number, and it gives you the largest number. And then someone will say, give me your largest number now, and it'll give you what was the second largest number. Alright, so how do we remove from a heap? This is a max heap. We want to give the caller the largest number in the heap. So where do we find the largest thing in a max heap? How do we locate it?
It's at the top.
It's at the top, guaranteed. Because the heap property says whatever's up here has to be bigger than both children, and each of these has to be bigger than its children, and each of those have to be bigger than its children. So this has got to be the biggest thing in the whole heap. So to remove the biggest value is easy. Just return the root. Alright, well, no problem. I'll just, take that off, give you 100. It's not a heap anymore, right? We got to have something at each level, all the way from the left to the right. So how do we turn this back into a heap? So what we do is we replace the root with some node from somewhere else in the heap. If we want to preserve the heap shape, what's the only node that we're allowed to remove from the heap?
Would it be the 60?
It would be the 60. If I remove the 35, it's not a heap shape anymore because this level isn't full. If I remove the 38, it's not a heap shape anymore because the lowest level isn't filled in from the left. The only thing I can remove and still have a heap shape is this last thing on the bottom row, the rightmost thing on the bottom row. So since I'm removing the 100, because that's the largest value that I just returned, and I need to replace it with something, I'm going to take this 60, and I'm going to put that up here at the root. Alright, I've still got a heap shape, but I don't have a heap necessarily. For example, 60 is not bigger than 90. So here's our remove operation. So we're going to return the root, right, after we replace root with last entry in the heap. Where by the last entry in the heap, I mean that thing at the lowest level furthest to the right. So we replace the root with that last thing in there. And then we do what's called downheap. And then we return, the root that we removed in the beginning. So how does the downheap work? So downheap basically begins from the root in this case, and we say, does this node satisfy the heap property? Is this bigger than both of its children? If not, swap with the largest child. So in this case, the 90 is the largest child, so we'll put the 90 here, and we'll put the 60 here. And then downheap from here. Does this satisfy the heap property? No, 60 is not bigger than both children, so swap 60 with the largest child. So this becomes 61, this becomes 60. There's no child under here. This satisfies the heap property. We're done, and we should have a heap. 90, 61, 50, 57, 60, 30, 35, and so on. So downheap. While the heap property at some node is not satisfied, swap node with the largest child, and then go back up there and check the heap property at that child. Alright, so if we want to remove another number from the heap, what are we going to remove? We're going to remove the 90. That's the largest thing in the heap. Now we're going to take the last thing in the heap, which is a 39, put it up to the root, and we're going to downheap. Swap 39 with the largest child. This becomes 61. This becomes 39. Swap 39 with the largest child, which is 60. This becomes 60. This becomes 39, and we've got another heap. Let me redraw this heap more clearly. 61, 60, 50, 30, 35, 57, 38, and child of 60 is 39. Right? Clearly a heap. Each node's bigger than its children. And it's still got the heap shape. Alright, do you want the next largest thing in the heap? That's a 61. Remove that. Take the last thing in the heap. Put that up to the root. And then downheap. Yeah?
What if you want to add, like, let's say you want to add the 100 back. How would you do it?
Okay, let's do that. Let me finish deleting since I already put it up there. But then let's go ahead and add. So downheap, swap with the largest. So this becomes a 60 and a 38. Swap 38 with the largest, which would be 57. So now our heap looks like this. 60, 57, 50, 38, 39, 30, 35, and there's our heap. Alright, so let's insert something. Let's put 100 back in. So to remove, right, we're going to return the root, we're going to replace the root with the last entry, and we're going to downheap. To insert, we're going to take our new number and put it into the last entry. So rightmost location on the bottom row, or if the bottom row is full, you know, rightmost location on the next row. So we'll put our 100 down here. And then we're going to upheap. And upheap means, you know, compare this node's parent and see if that satisfies the heap property. Well, 38 does not satisfy the heap property. It's not bigger than its children, so we'll swap 138. And now we'll see if 100's parent satisfies the heap property. Is 57 bigger than both children? No, it's not. So we're going to swap 57 with the largest child. And now we'll check 100's parent and see if that satisfies the heap property. Does 60 satisfy the heap property? No, it's not bigger than the largest child. So we swap it with the largests. And now we have a heap again. And drawn more neatly, it looks like this. So we've got a 60 over there. Our 39 is still here. Our 57, and there's our 38. So to remove, you just return the root, right? Replace the root with the last thing in the heap and downheap. To insert, you add to the last position and you upheap.
Can we go over like what makes a tree balanced? Because you did mention earlier that that heap cannot be unbalanced. So, and at first I thought the 60, 57, 38 that you got from inserting tree caused it to be unbalanced. But
This?
is it yeah? But would you have to add one more thing to 38 to be unbalanced?
If I added something down here or down here, that would unbalance it, yeah.
Okay.
But if I added something off the 57, it should still be balanced.
Yeah, because because 57 could be considered a new root in for that subtree.
Right, right.
Okay.
Yeah. So these operations are pretty efficient. Right? How much work do we have to do to remove the largest thing from a heap? Roughly how many steps do we end up doing? Say, worst case. So when I remove the 61, what do I have to do?
I was thinking it could be like log of n operation.
Yeah,
For some reason.
it actually is exactly log n. Because
I think that because of log base 2 and how it takes like I think remember you going this from the past where the tree is kind of the number of steps of trees is like 2 to the power of n. Well, 2 to the power of n is the number of steps in the tree, but it's like it's the log base 2 of that.
Yeah.
It's the number of steps. Okay.
yeah, so our work is defined by the height of the tree, right? Returning the root, well, that's just one operation, right? Just return the root when you're done. Replacing the root with the last thing, well, that's just, taking this and moving it up there. And then downheaping is the only sort of loop we have. And to downheap, we have to move down at most, the height of the tree. And the height of the tree is proportional to log n. And so it's a fixed amount of work plus log n. So insertion and removal from a heap are both log n operations. And that's pretty cool.
Will there be a scenario where you have to do a removal and inserting from the right subtree? Or is it only for the left?
When your heap grows, I mean, if our heap looked like this and we wanted to remove the 100, we'd be replacing with, this node right here. But it's not because it's in a left or right subtree per se. It's because it's the rightmost thing at the lowest level. And when we want to add something, if our heap looks like this, we'll add it right here. If our heap looks like this, we would add it right here. And so it's not like the delete from a binary search tree where we take the largest thing in a left subtree, for example. It's just taking the last thing in the heap, right? Meaning the rightmost thing on the lowest level. Does that make sense?
Yeah, I'm just wondering about like how you able to keep track of, or how would you know like where to put the 100 in this case in the bottom of the tree?
Yeah, so we will look at an implementation for this that's really slick.
Because I'm just raising a lot of questions about this of like all the what ifs.
Cool, that's good. Yeah, so we'll go through implementation in a little bit, and we'll see a happy surprise. All right, so insert and removal order log n operations. So on par with binary search trees where you have to recurse downward, and worst case you get to a leaf node, and the amount of work you do is on order of the height of the tree, which if the tree is balanced will be order log n. Heaps are always balanced, right? So the amount of work it takes to get down is basically log of the number of stuff in your heap. Which again, is really nice because, a trillion nodes in your heap, it's got a height around 40. So 40 operations go through your loop 40 times, and you can complete your downheap or your upheap. All right, and min heaps are the same, except you're going to have the smallest thing at the top. But again, to insert, you put something in the last spot in the heap, and you upheap. To remove, you remove the root, and you downheap. All right, so suppose you have a bunch of data and you want to build a heap. Suppose you...
Sorry.
Yeah, go ahead.
Have you talked about you talked about max heaps? Have you talked about like mini heaps or I forget what you call them, but have you talked about that yet? Covered it?
Yeah, that's what I just said. Actually, was a min heap's exactly the same, except you check the min heap property, but you do exactly the same thing. You remove from the root, and you insert by putting something in the last location, and upheaping. You remove by removing the root and replacing it with the last thing and downheaping. None of that changes. The only thing that changes is the heap property that you're checking is now you want to be smaller than both of your children. So let's make a min heap.
Yeah, I was gonna say, give us an example.
So if you want to remove the smallest thing in this min heap, right, that would be a 10. We'd replace the 10 with the last thing in the heap, which is a 35. And then we downheap, testing for the min heap property. So the min heap property says this should be smaller than both of its children. Well, it's not, so we swap with the smallest child. So the smallest child is 20, so we put 20 at the root, bring the 35 down. Check the min heap property. Is 35 smaller than both children? No, it's not. So we swap with the smallest child, which is 25. And we're done. This satisfies the min heap because it has no children, and so we've got a heap again. And now our heap looks like this. And each node is smaller than its children. And the only thing, if we're looking for a min heap and we have a 50 and a 40 and a 30, right? To downheap, right, we need to swap 50 with the largest child. If we swap 50 with the smallest child, right, it's still not a heap, right? Because, oh no, that is, yeah, swap with the smallest child. If we swap with the largest child, so if we swap the 50 and the 40, it's not a min heap, right? This is not smaller than both children. So for a max heap, swap with the largest child. For a min heap, swap with the smallest. All right, so building a heap. So you have a bunch of data and you want to put it into a heap so that you can start extracting data. We'll go back to max heaps. So we can start extracting data largest to smallest. And so one way to do this is just start with an empty heap and keep inserting data. So we could just, take the first number you want to put in your heap, add that to an empty heap, that becomes the root. Take the second number, put that at the end of the heap, swap it with the root, downheap, and so on. And if we do that, we know that each insertion takes log n operations. And if we have n numbers we want to insert, that'll take us basically n log n to build a heap of n pieces of data. But there's another way to build a heap. And that's to do something called heapifying. And so let me just pick off some randomish numbers. So I'll go back to the numbers we had for our quicksort. So let's I should do this with pencil. we're going to take our data, we're just going to throw it into a heap shape. Right? So the data is coming in this order. So I'm going to take a 4, a 131, an 8, a 51, an 18, a 37, an 11, a 7, a 9, and a 20. Alright, so first thing I'm going to do, I'm going to take my data as it comes in, I'm just going to throw it into a heap shape. And now I'm going to do an operation called heapifying. And heapifying begins with the last thing in your heap and basically asks if its parent satisfies the heap property. Alright, so we want a max heap. Sorry, that's not what heapify does. Heapify starts with the last number and it downheaps from there. Alright, so 20 has no children. It satisfies the heap property. We don't have to do anything. 9 has no children. 7 has no children. No work to do for these leaf nodes. 11 has no children. No work to do there. 37 has no children. No work to do there. The first node we have to do any work on is 18. So let's downheap from 18, which means does 18 satisfy the heap property? It doesn't because it's smaller than 20. So swap 18 with 20. And 18 is a leaf, so that satisfies the heap property. We're done. Here's a 51. Does this satisfy the heap property? Yes, it's bigger than both children. Nothing to do there. Go back up one more level. Here's an 8. Does that satisfy the heap property? No. Swap with the largest child. So this becomes 37 and 8. And we're done. 131. Bigger than both children. We're done. And then come up to the 4, and does that satisfy the heap property? No. So swap with the largest child. Does 4 satisfy the heap property? No. So swap with the largest child. So this will be 51. And 4, does 4 satisfy the heap property? No. Swap with the largest child. And we're done. We're out of nodes. We've got a heap. And our heap looks like this. 131, 37, 8, 11, 51, 9, 20, 18, 7, and 4. And there's our heap. So this is heapifying, and it's a really efficient way to build a heap. Alright, so again, to build a heap out of a set of data, first just throw your data into a heap shape, and then beginning with the last element in the heap, do this heapifying operation, right? Basically see if this satisfies the heap property. If it doesn't, downheap from there. And just work your way back from that last node all the way up to the root node. And at each point, see if it satisfies the heap property. If it doesn't, swap with the largest child in this case and keep moving down. And when you're done, you end up with a heap. The cool thing is the order of complexity of heapifying a set of n elements. And you know, at each of these points to downheap, we potentially have to swap a node with, you know, a largest child all the way down to the bottom of the tree. That's theoretically a log n operation. And we have n nodes which we have to potentially do this for. That sounds like n log n again, which is the same as just doing n inserts into a heap. But it turns out heapifying is actually an order n operation. And that's fantastic. The reason it's order n is basically this. Suppose you have a heap. And we'll make a nice full fluffy heap. So we have 15 nodes in here. The height of the tree is 3, the number of elements is 15. Alright, these 8 elements I don't have to do any work for. They all satisfy the heap property. Well, that's half my data, right? Half of my data will be at that lowest level. So half my data, I don't even have to do a single operation. This next level up, if this turns out to violate the heap property, I only have to do one operation. I swap with the largest child, and then I'm back to a leaf node. So for everything at this level, worst case, I have to do one operation. And at this level, I have, you know, another quarter of my data. I have half of my remaining data. So 50% of all my data, I do no work for. Another 25% I do one operation for. So if I have 1 trillion pieces of data in a heap, 500 billion of them I don't have to worry about. Another 250 billion of them I have to do one operation to heapify. And I've only got 25% of my data left over that I need to worry about up here. And half of that data that's left over, I only have to do 2 operations. And so if you run through the analysis, and it's actually a fun algorithm with infinite series and converging inverse exponents of powers of 2, you find out that heapifying n pieces of data is actually order n. And that's pretty slick. Alright, so let's talk about implementing a heap. And you know, we can implement with a binary tree. We can have left children and right children and use the stuff we've been doing so far. But that's not terribly efficient. There's a few problems with that. One problem is finding this last thing in the tree. And how do we find, you know, the last thing in the tree if we don't have some kind of left-right structure, right? I mean, starting from the root, should I begin by going to the left or going to the right? Well, you know, if I happen to have something over here and something over here, the last thing in the tree will be something I find by going to the right of the root. But if this is the last thing in the tree, I should go to the left of the root. So even just finding this last thing is problematic. And maybe I could have a pointer that points to it or something. But trying to find your parent, right, when you insert something here and then you need to move up, you need to find your parent. You need back pointers telling you where your parent is and so on and so forth. So a tree implementation like we've been doing with a data value and then a pair of pointers to left and right really doesn't work very well here. But I'll tell you what works great is just a plain old array. And so let me make a heap. There's a heap with 10 things in it. And let me make an array. Let me put some indices on here. And I'm just going to store the contents of my heap into my array in order, starting from the first node, moving from left to right, and then going down. But I'm going to start storing at index 1. I'm not going to use index 0. I'm going to store my nodes as A, B, C, D, starting at index 1. And now manipulating my heap is really, really easy. So let me call this, you know, H, or heap. Well, the root's easy to find. It's always at location 1. And let me have, you know, some variable end, which tells me the index of the last element in my array. And so last node is just heap bracket end. So my last node is node I, for example. Now, if I have a node at index n, what is the index of its parent? For example, E is at index 5, its parent B is at index 2. D is at index 4, its parent B is at index 2. H is at index 8, its parent D is at index 4. So is there a rule for finding the index of a parent, given the index of the child?
Just one left? Or
It's
no?
just n over 2. And the left child of node n is 2n, and the right child of node n is 2n plus 1. So node 1, the left child is 2, the right child is 2 plus 1 is 3. Node 3, which is a C, the left child should be 2 times 3 is 6, that's an F. The right child is 2 times 3 plus 1 is 7, that's a G. If 2 times n is bigger than n, then it has no child on the left. If 2 times n plus 1 is bigger than n, it has no child on the right. So with some simple index arithmetic, I can move around my heap really, really easily. I know where the root is, that's element 1. I know the last node, that's element end. The parent of a node, just take the index divided by 2. The children, just take twice the index and twice the index plus 1. And so if I want to insert something new into my heap, I simply increment end, and I store my new data at that index, and that creates something like this. And if I want to find that node's parent, just take 10 divided by 2 is 5, tells me the parent is E. And if I want to find E's parent, 5 divided by 2 is 2, that's B. And if I want to find B's parent, 2 divided by 2 is 1, that's A. So I can upheap after my insert, and I can swap, and I can find both children using this arithmetic. And so a really, really fun, easy programming exercise is implementing a heap using an array. And it turns out to be a lot more efficient than using a node like we've been using with left and right children and so on. And so heaps are a quick go-to if you want to sort data and you want to extract data in a particular sort order, largest to smallest or smallest to largest. If you have all that data to begin with, you can heapify it. It's an order n operation, and then order log n to pull out each item. This is also useful if you have data that you want to continually add things to in some sort of random order, but you want to remove things from, say, largest to smallest or smallest to largest. And one real-world example of that would be something like a priority queue. So in a job scheduling system inside an operating system, you have a list of jobs that are being executed, and you go from one to the next, but your jobs may have different priorities, right? So if you look at jobs on a Linux system, there's a priority value, right? Negative numbers have the highest priority, 20 is the lowest, or a lowest. And so when it's time to pick another job to execute, you might want to go through a list of all your jobs and find the job that's available with the highest priority. And a max heap would be a great structure for doing that. And then when a new job comes along, you simply insert it into the appropriate heap, right, which is a log n operation. And meanwhile, your operating system job dispatcher is pulling things off of the heap, taking the highest priority entries first. So heaps are useful for all sorts of good stuff. All right, that should give you enough to do the heap quiz on Canvas. And that's pretty much the end of the material I had planned for 222 for winter quarter. So there's a few things we'll pick up in 223 that sometimes I do in this quarter, but 223 will be, you know, advanced data structures, and it'll be a focus on Java. All right, so that's pretty much it for material. Come to office hours if you want to go over questions on assignments and such. And Wednesday, I am just planning to have for review. So if you have questions, bring them then. Otherwise, you'll have to listen to me talk the whole time and just kind of rehash everything we've done. So questions will be better. If you got your hand up, yeah, go for it.
Isn't the hash quiz, or not hash, heap quiz, isn't the due date already passed?
Yeah, so I mentioned that since we're getting to this stuff later than I had planned, as long as you turn it in by the 11th, which is when it closes, it will still take it, and you'll get full credit for it. So you got a few more days. All right, cool. Have a good one then, and I will see everybody next time. Thank you.
Bye.
Alright. Do you have